Okay, we're going to start chapter 4 today, and we're going to begin by talking about one-to-one functions. Okay, so we've been talking about functions for a long time, right? Ever since circles. Remember what it means to be a function. Every x value corresponds to exactly one y value. So this is a function because every x is going to its own y. It did not matter if more than one x went to the same y, as long as every x went to its own y. But now we're going to restrict that even more and talk about one-to-one functions. And one-to-one functions, it's still a function, but each x value corresponds to only one y value. And each y value corresponds to only one x value. Okay, so the first bit of that is just saying you got to make sure it's a function to start with. And then also, in addition to make it one-to-one, each y value corresponds to only one x value. So now, even though this is a function, it's not a one-to-one function. This one, however, is one-to-one. Each x goes to its own y, each y goes to its own x. Okay, so one-to-one functions. To decide whether, when we have an equation, whether they're one-to-one, okay, basically what we're doing is looking for anything that makes the x value have the same, go to the same y value, whether it's positive or negative. So a square on an x or an absolute value on an x, something like that. Recall when we were looking for functions, just to see if it's a function, we looked at the y and we said, hey, if it's got a square on it or an absolute value or something, it's not a function at all. Now to see if it's one-to-one, after we determine it is a function, so the y is okay, I look at the x value. Okay, because this has a square on it, then my proof to show, I already know it's not a function, so my proof to show that is let's pick a number, right? So let's just pick f of 3, just because I know that'll work out nicely. You can pick f of 1, it doesn't matter. Just pick a number and plug in the square root of 25 minus 3 squared equals the square root of 25 minus 9 is 16. So f of 3 equals 4. Or if I plug in f of negative 3, okay, the square root of 25 minus negative 3 squared is the square root of 25 minus 9, or the square root of 16. So f of negative 3 also equals 4. Can't have this. Can't have f of 3 equal 4 and f of negative 3 equal 4. When x is 3, y is 4. When x is negative 3, y is 4. No, not a function. Okay. But if I don't see anything obvious that makes it not a function, then I can say, well, how do I prove it is a function? All right, well, let's plug in an a and find f of a, which means we'd have negative 4a plus 12. And then let's plug in a b and find f of b and set them equal to each other. Okay? Because my proof of whether something is a function is if f of a equals f of b, then a must equal b. If this is not true, it's not a function. So here's f of a. We've set it equal to f of b. Let's see what happens when I try to solve this. First thing is, let's subtract 12 from both sides. All right, to get negative 4a equals negative 4b. Divide both sides by negative 4, and you get a equals b. Oh, look, if f of a equals f of b, then a equals b. That's proof that this thing is a function. Even though really we already knew it was, because We couldn't find two x values that equaled the same y values. But so here's how you can prove it, right? And if you know it's not, here's how you can prove it's not. Find two values and show that different x values will give the same y value. Okay, now if we're looking at the graph, remember to determine if it's a function, we have that vertical line test. If it's a one-to-one function, it will also pass the horizontal line test. Look, this is the graph of the one we just said is not a function, square root of 25 minus x squared, so they've graphed it for us, right? And here's those points we found, -3, 4, and also +3, 4. Okay, so if it doesn't pass the horizontal line test, it's not a function. Now, don't forget, first of all, we got to make sure it's a function. Okay, so let's think about our square root function. Function, also one-to-one. Let's think about our quadratic function. Function, not one-to-one. Okay, and once again, it's a quadratic, it's got that square on my x if I were looking at the equation. Okay, this typical one, the basic one, does not. Now here, they have made it not one-to-one. All right, so determine whether these graphs are one-to-one. And really, they've already done the work for us on this, because here's the vertical line test, and they're showing that, hey, it's not one-to-one. This is not a one-to-one function. Notice this could be a cubic, could be a fifth degree or whatever. So some cubes, your basic cube, are one-to-one, but some are not, where we have that extra, x cubed plus 3x squared, right, blah, blah, blah. This one is just a plain x cubed. It is one-to-one. All right, and this function is one-to-one, right? They've drawn a vertical line through it several times. There's no place you can draw a horizontal line, There's no place you can draw a horizontal line through it and cross that function more than once. Okay, so now that we can identify one-to-one functions, let's talk about inverse functions. And the reason that follows is because for a function to have an inverse, it has to be one-to-one. Okay, for a function to have an inverse, it has to be one-to-one. Okay, so well, I'm not sure why they didn't talk about that first, so let's talk about that first just a little bit. Okay, so a one-to-one function, let's use the cube, and its inverse, the cube root, remember, looked like this. Need a little bit better flat place there, but okay, looked like this. So this is its inverse. X cubed and the cube root of x, they undo each other. We think of them as being opposites, but the mathematical term is inverse. Okay, so this is one-to-one, so it has a nice inverse. Or think about the x squared and the square root. Remember, we said technically this is x squared, but if we did the y squared, if we did completely opposite, it looks like this. This thing does not have an inverse unless we put a restriction on it, right? We can restrict this to only being half of this function, and then it has the inverse of the square root, right? All right. So if we have a function that's one-to-one, right, then for any value of x, f of g equals x and g of f equals x. Right? Remember that notation we had before. F of g of x equals x and g of f of x equals x. Then they are inverses of each other if these two things hold. Remember, this means I'm just going to plug the g into f. If everything gets undone and you're just left with an x, then you go back and you plug the f into g and everything gets undone and you're just left with an x. Oh, those are inverses. Right? Those are inverse because they undo all the operations of the other one. Think about that x cubed and plugging it into the cube root of x. So if you replace the x with x cubed, oh yeah, they're going to undo each other. Okay, the other way, if I had this function and I plugged it into a cube function, they're going to undo each other. All right, that stupid pen is back. Yay, okay. Sorry, but that pen up there annoys me. Okay. So, you're going to have questions where it says, okay, is g the inverse of f? In other words, are these two functions inverses of each other? And you're thinking, well, let's see. To find out, we're going to do f of g. So remember, f of g means I'm going to start with f, but everywhere there's an x, I'm going to put g. So instead of just x, I'm going to put the cube root of x plus 1, and then this x is cubed, and then I have minus 1. Okay, now, just simplifying that, my cube root and my cube will undo each other and just leave x plus 1 minus 1. Plus 1 minus 1 is 0, so f of g equals x. So far, so good. If g of f is also x, then yes, they are inverses. If one of them does not equal x, if you get anything but x, then you say no, they're not inverses, right? So if I would have gotten anything else here, I wouldn't have to do this. But if I get x, then I got to keep checking and say, well, let's see. So g of f means I'm going to start with g. And everywhere there's an x, oh, here's an x, I'm going to put f of x. Okay, now as I simplify, okay, I'm going to get rid of those parentheses. So x cubed minus 1 plus 1, well, minus 1 plus 1 is 0. So I just have the cube root of x cubed, which will undo each other. Okay, yes, these two functions are inverses of each other. Okay, all right, so far, just to keep up, before we even talk about inverses, we got to see if your function is 1 to 1. Okay, if your function is 1 to 1, and you want to know if the two functions are inverses, you plug them into each other, f of g and g of f. If you get x, then yes, they're inverses. If they're not 1 to 1, they don't have an inverse to start with. So don't forget to check that first. As soon as you see they're not 1 to 1, then nope, they're not inverses because they don't even have an inverse. Okay, now we get special notation for inverse functions. It's written like this. And it has nothing to do with an exponent, right? It's not a negative exponent. It's just a special notation when it's on an f or a function notation, and it's read f inverse. So I could say f of x is x cubed minus 1. Then f inverse of x is the cube root of x plus 1. If f of x is cube root of x plus 1, then f inverse of x is x cubed minus 1. They're inverses of each other. Okay, by the definition of inverse functions, oh, this is going to be important for us also. The domain of f is the range of f inverse. And the range of f is the domain of f inverse. Right? So the domain of one function is the range of the other. And then the range of that function is the domain of the other for inverse functions. So that's going to be useful. Let's try to remember that. Okay, so now let's talk about, okay, well, let's find the inverse of some functions. First of all, I got to make sure it's a function. Okay, so if it's a function, that means if I'm looking at a set of points, all the x's have to be different, -2, -1, 0, 1, 2. If it's a one-to-one function, all the y's have to be different also. 1, 2, 2. Okay, no inverse exists because it's not one-to-one. So there is no inverse. Let's check this one. 3, 0, 2, 4 makes it a function. 1, 2, 3, 0 makes it a one-to-one function. So if I'm going to find the inverse, all I do to find the inverse is trade places with my x's and y's, right? The domain of one is the range of the other. The range of it is the domain of the other. So all you do is trade places with your x's and y's. 3, 4, 3, 0, 2, 4. Okay? Okay. So that's what they're saying here. The inverse of a one-to-one function, got to be one-to-one, is found by just interchanging the x and y values of each of its ordered pairs. Okay? If we have an equation, we do the same thing. So here's the steps. It's very short, very simple process to find the inverse of a function. If it's written with function notation, replace f of x with y. Change places with x and y, and then solve it for y. Most important step that people forget most is replace y with f inverse at the end. And as we do one, we'll talk about why that's so important, and we'll see how it's so easy to forget. Okay. So this says, first of all, decide if each equation is one-to-one. Even if the instructions don't say that, if it just said find the equation of the inverse, that's your first step. Is it one-to-one? This one is one-to-one. I don't have any squares or anything making it not one-to-one. Oh, look, this one's not one-to-one. So I already know there's no inverse. There's nothing to do here. Okay, this one's okay. Odd exponent's okay, not even. So no inverse here. So first step, make sure your function is one-to-one. If it's one-to-one and we're asked to find the inverse, replace the f of x with y. Okay, notice if I were working on this one, I wouldn't have to do that step, but if it's using inverse notation, replace the f of x with y. Just exchange the x and y values. Just trade places with them, right? So let's make this x equals 2y plus 5. Then solve it for y. So let's subtract 5 from both sides. So x minus 5 equals 2y. Let's divide everything by 2. Okay. So I get y, and once it's by itself, I'm going to flip this around. And you can either leave it like this, or you can make it 1/2 x minus 5/2. It doesn't matter, right? Either one of these, perfectly fine. Then the last step. Now, a lot of times people say, oh, I got it solved for y, and they stop. But this is why it's important to go back and put in your notation. Y is not 1/2 x minus 5/2. Right? The function is not this. Here's the function. Y is 2x. I can't in the same equation say y is two different things. So, oh, okay, yeah, that's y. That's f of x. This is the inverse of y. So don't forget I got to put that function notation back in. Okay, now these two are opposites of each other. They're inverses. Let's do the same thing over here. We know it's 1 to 1, so let's replace f of x with y. Let's just trade places with that x and y. It's the only time I can do that. It's not a valid algebraic step or anything. It's just in the process of doing something. And let's solve for y. So I'm trying to get this by itself. So I want to cube root both sides. Whatever I do to one side, you got to do the same thing to the other. Okay. And this is a cube. So these will undo each other. And just leave the cube root of x equals y minus 2. Let's add 2 to both sides, getting that y by itself. Okay. Once the y is by itself, I'm going to put it on this side. And we have the cube root of x plus 2. And what's the most important step? Replace that with function notation. Okay. Now I have the inverse of that original function. Okay, so very simple process. Okay, 2 important factors: make sure it actually has an inverse, and then replace the y with your function notation in the end. Okay, if we're trying to find the graph of an inverse function, looks like they've already actually done it for us, but that's okay. It's real simple. We're still just going to change places with x and y. All right, so here's the function f, right? This one is f, the blue one. So if we're looking for f inverse, now they have it graphed for us, but all you have to do is find some points, enough points so you know the shape of the graph, right? So if you have a cube and you're trying to find the inverse of it, depending on, where it's located on your axis, you need several points. And once you find those points, all you do is trade places with the x and y value. Okay? So because this is a line, I just need 2 points. So I see, oh, if here's a point -4, 0, then the point 0, -4 is going to be on my graph of my inverse. Here's the point 1, 3. Then I just plot 3, 1. So once I get those 2 points, I can draw my line. Okay, so same thing over here. Here's the actual function. So I'll find a couple of points. Here's the point 0, 0. Here's the point 1, 1. And here's the point 2, 4. That means on my inverse, I have 0, 0 and 1, 1 still. But instead of 2, 4, now 4, 2. And I can draw it in. Okay, so inverses, you just change the x and y, right? Just change the x and y. Notice another feature of these graphs: if you drew the line y equals x, then these are the mirror image, right? They're flipped. If you imagine folding this graph over this line, it would lay down on the inverse. The function and the inverse would lay on top of each other. Here's the line y equals x. Imagine folding this over that line, right? This would lay on top of that. This part would lay on top of that. So I could also use this idea if I wanted to. It's easier to just find some points and change the values. But if I don't have any points, I can draw this line y equals x, and then just imagine drawing, and that those points will be perpendicular to this line. So just imagine drawing a point perpendicular to that line and the same distance away, right? And we'd get our points that way. Okay, now This says find the inverse of a function with a restricted domain. So sometimes, like we talked about that function f of x equals x squared, technically it does not have an inverse, right? Because it's not one-to-one. But if I restrict the domain to where x is only greater than 0, where the graph looks like this, just half of that parabola, now I can find its inverse. So this was already one-to-one, right? But you'll probably notice that its inverse is going to be some kind of square function. So it has to be 1-to-1, right? All right. So we're going to do the same thing. We're going to replace x with y. Well, first we're going to replace f of x with y. Okay, I don't really have to worry about that restriction yet. Okay, then trade places with x and y. Solve for y, meaning I need to get this by itself, so I need to get rid of this square root. Square both sides. So x squared equals y plus 5. Still trying to get that y by itself. So now that the y is by itself, I'm going to put it over here. And don't forget to change that notation and put it in terms of your inverse notation. All right. Now, that means these are inverses of each other. But notice this doesn't even have an inverse. So it's got to have some restriction. Remember we said the domain of one is the range of the other, and the range of one is the domain of the other. So if I go up here, I know my domain here. But what's my range? What can y be? If I go up here and I plug a -5 in, okay, -5 in here, that makes a 0. Okay, if I plug a -6 in, right, then that makes, not a -6, it's got to be greater than -5, so a -4 in, so square root of 1 is 1, so I've got 0, and all the numbers in between 1, right, okay, that's my range up here, so that's my domain down here. X has to be greater than or equal to 0, and my range for down here is x is greater than or equal to -5, okay? So I can go up here and find my range of my original function, and that'll tell me my domain or my restriction on my domain down here. Okay, so notice, right? We got that by saying that has to be greater than or equal to 0 for one thing. Okay, that's why we got our domain here. Okay, so here's some important facts about inverses. I think this is probably our last slide. If f is 1-to-1, then it has an inverse, okay, which means if it's not 1-to-1, it doesn't have an inverse. The domain of f is the range of f inverse, and the range of f is the domain of f inverse, and we just saw why that's useful. If the point AB is on the graph of f, then the point BA is on the graph of f inverse. They're also reflections of each other across the line y equals x. To find the equation for f inverse, change f of x to y and trade places with x and y. Solve for y. Okay, guys, that's it for this section. I'll see you next time. Let me know if you have questions.